Welcome to Oxpoon, the technology magazine. Hello and welcome. That doesn't sound as nice as a gong, but it has a deeper purpose. Because a hammer blow like this, on an artificial stone in this case, allows trained ears to recognize whether everything is in order with this stone, or whether there may be cracks in it or other signs of wear and tear. This means whether this stone promises stability or not. It is an artificial stone. What does that mean? So it's not a stone that has grown in nature, that we humans have taken from nature and then processed, but we have made it ourselves with materials. And people have been doing this for a relatively long time. The oldest archaeological excavations, the oldest archaeological datings that can attest to people working with concrete, which means making their own building materials, date back around 3,000 years. So there is evidence from Egypt, from pyramid construction. And then came the Romans. And they were known for doing everything very meticulously. And they built a lot with concrete. And above all, it was always a science for them. What materials do we have to work with? How do we have to process them? And so over the centuries, one can say, perfection has continued to increase over the centuries. These were the old measures with concrete, and the old variants of concrete. And if we want to make concrete now, then we take some cement, for example, like in a sand pit, so to speak, and take sand here. And I'll save myself the mess here in the video. If we were to add water, mix it well, and let it harden, then we would have a solid concrete mass. That's an example. There are many, many different types of concrete. And yes, in the 18th century or thereabouts, in the middle of the 18th century, that's when modern concrete emerged. And then people used completely different scientific methods than had been the case in the centuries and millennia before. And concrete was used for all kinds of applications. So if it had to be particularly light, or if it had to be particularly resistant to pressure, different materials were found, different additives were found, which we put into the concrete to achieve the desired properties. But the fact is that everything we use, everything we produce, ages. And on the one hand, the aqueducts and the Roman buildings and also the pyramids still exist, which is a very impressive achievement, and also demonstrates the skills of the people back then. But as we can also see from this stone, this artificial stone that I have brought with me, it has definitely seen better days. It's not that old yet, but we can see that it has a structure here. It is, you could say, quite ruffled on the sides. And we have to be able to check the safety of our buildings, where safety in our lives is concerned. For example, when it comes to road structures, buildings, we have to be able to check whether there are cracks, whether something has changed, whether the concrete is getting old and brittle. But how can this be determined? I already hinted at it at the beginning, and I checked my kitchen cupboard and looked to see if I had something with a corner off. And as we can see here, I found a plate that is no longer in perfect condition, but is perfectly usable as a test object. If I take this plate and let it swing freely and strike it with a mallet like a bell, then it resonates in a very, very specific way, with a very specific sound. If I take a second plate, and you can see that this is a plate from the same series, same pattern, same material, and my mallet has also remained the same. If I let it swing freely again and strike it again, we have a different, more tinny sound. And in this case, we can even see it visually. If we look at the back of the plate here, this plate definitely has a crack. So we see this pattern, these cracks at the bottom here, and that's why. The sound is reflected by the cracks. And it is precisely this process that we use nowadays when we want to test concrete. There, too, the sound is reflected by the cracks. And with modern, highly specialized equipment, we are able not only to hear this by ear, but also to analyze it. Modern devices that send ultrasound through the concrete, through the material, and can listen to the responses of this ultrasound like a radar, like an echo in a radar, record it, analyze it, and determine it over time, determine where a crack is, and where the next crack is, and so on. And I've had a look at these modern devices. I have brought you the PCE PMI4 concrete moisture meter. And when we switch it on, we see a nice, large, easy-to-read display. And I'll let you take a look at the back. We have some sensors here that are attached directly to the device. I can also show it here from the side. And the idea, the approach is as follows. I've brought an artificial stone here, and if I want to know how much moisture is in this stone, then I go and place the device on it and press it down. And now you can see in the camera, if you look closely, you can read the value of 3.8%. But if you are somewhere where you can't read it easily, because you have to work on a concrete pillar or something similar, then you have the option of pressing the hold key here. And then this value, the maximum value, is saved. The display changes the colors, makes them inverse. Then you know that the maximum value has been reached. And you can remove the device from the spot, from the measuring location, and read it off easily. The device is able to analyze different types of concrete or mixtures. So here we see cement screed. I can also go through further. Anhydrite screed. And we even have plaster back here. It measures with an accuracy of 0.5% up to a range of 6% moisture. Not with all materials, but with concrete it can detect up to 6% moisture in the material. The PCE PMI4 is a nice, small, handy device with battery operation, so you can take it with you on the go. Here on my stone is the PCE HT225A, a so-called concrete strength tester. And I'm putting it here because that's the way it's used. This device works according to the Schmidt measuring principle to test concrete hardness and compressive strength by simulating a rebound. And we can take a look at that. We can demonstrate that. So I have to unscrew a cap here, which is on the trigger for safety reasons. And then we do the following. This emery stone is included in the scope of delivery. And when I take it, I sand the spot, the area. I want to measure. So then, I take the device in my hand. To make the measurement, I now press the device down slightly until the safety catch releases, and the tip then extends. And in the next step, I press the device down. And be careful, don't get startled. We have taken the measurement, and I had to press the button at the top to stop the measurement, to save it here, so to speak, in an analog way. And we see that our measurement result is 40. What does 40 mean now? Well, that's quite simple. We simply turn the device over, because we can then interpret the value on the back. We have a little drawing up there that tells us that we can measure at completely different angles. So once plus 90 degrees, which means, as I measured, from top to bottom. Or we can also measure sideways on a wall, and we can even measure from below on a ceiling. Because you can't access every building from every side. That would be too nice. And yet we are dealing with gravity, and we have to take an adjustment factor into account here. And we can see up here, When the camera goes a little further up, that's where we see the angle drawn in. So we are at plus 90 degrees, and we have a value of approximately 40, and now we see 295 back here. And the value is expressed in kilograms per square centimeter. The device is able to measure from 100 to 600 kilograms per square centimeter. And it is not only used for the actual purpose, i.e. for the hardness of stone and concrete, but also for the winding test on things that are wound onto rolls, to check how good the winding is. A nice simple analog device, the PCE HT225A. I have brought you the PCE UCD100, a device with an easy-to-read 10.1-inch TFT display, which is suitable for material testing with ultrasonic sensors in concrete to determine where there are cracks, where there are cavities in the concrete. You can see from the display that it is very easy to operate, and, above all, we can display and analyze the data immediately when we are outside, when we are at our measurement object. And I can start a measurement. So this is about testing the strength of the concrete, and I start this measurement. And you can see, you might also hear a ticking sound, and you can also see that measured values are coming in at the top of the display. These readings are now coming from these two probes that I'm holding here. And of course, we don't have the opportunity to test a large concrete pillar here in the studio. So this is a demonstration setup that doesn't produce any really meaningful measured values, but it's certainly still valuable for demonstration purposes. If I now hold the two probes onto the stone here, we can see that corresponding curves appear on the image. I take them away again, and the curves disappear. And that's also what we see on the right. The device helps us with this, so it shows us this. The opposite test mode is there, i.e., on opposite sides. There are other test modes that we can set, depending on what we need, depending on what requirements we have on site. But that's not all this device can do. When I switch off these probes and end the measurement here, we go to the main menu. And there it also asks us whether we want to save it or not. I say I don't want to save the measurement. If we go down here to the item for the width detection of cracks, we get this menu. And I click here or press preview here. And now we can see, yes, it almost looks like a map. This image, the camera pans over here. This image comes from this module, from this camera, which is connected to the device, which is a very detailed, so you see, the camera is illuminated. And this camera now provides a very detailed image of the surface of our concrete. With this camera, it is possible to look at the crack depth and the crack width in detail. This detector comes with a coupling gel. And this is very important so that our sensors have good contact with the concrete, with the material, and in the way that the connection is guaranteed. It has 8 gigabytes of built-in memory for the measurements that we have made. It has a USB interface down here for data transfer and to be charged. The device comes with a built-in rechargeable battery, but it can also be operated with an external power supply. And it has a measurement interval of 0.05 to 409.6 microseconds, with a resolution of 0.05 microseconds. And it can induce various test voltages, from 120 volts to 1000 volts. And all this with a measurement range of plus, minus, up to 1.6 million microseconds. In other words, the PCE UCD100 is a real professional device that can be used universally. Let's take another look at the 3 devices. Firstly, the concrete moisture meter, the PCE PMI4, a small handy device with an easy-to-read display that can also be used to measure in hidden corners. The measurement can be saved and read off afterwards whenever it is convenient for you. Next, we have the PCE HT225A, a stable, robust, mechanical measuring device for testing the concrete strength according to the Schmidt measuring method. And last but not least, the large device, the PCE UCD-100, the ultrasonic concrete detector, which is able to detect and localize cracks and also locate cavities in the concrete, and with which you can analyze on site directly on the device where the problem is, what the nature of your material is. The whole thing together with a coupling gel, with sensors and also with a camera with which you can go to the surface in detail and analyze the surface. That's it for today. I wish you a day that is not at all concrete gray. See you next time.
Discover and order the latest measuring and test equipment now on www.pce-instruments.com.